So quick background, Casey Dreier, that's me. I work at the Planetary Society. Hopefully all of you know it. Hopefully all of you are already members. But we're a nonprofit independent organization promoting space science and exploration. So I run the policy and advocacy program. Today I'm really going to be wearing my policy hat. So one of the services we try to provide at the Society is just high quality data to help people understand the history of planetary exploration and really what it takes to enable it. So today, I'm going to talk about this project that we put together just this year. It really dives into the history of funding for the program at a granular level. And why is that important? So most of you, if you're planetary scientists, tend to be focused on the future or the currently operating missions for planetary exploration. But understanding what it took to get to this point, I think is really important, particularly if you want to get more of it going forward. So obviously, understanding the history of costing is really important to making an effective advocacy effort. So if you want to see more planetary science, if you want to see more exploration going forward, and you have ideas about where you want to go, whether it's increasing discovery missions, whether it's more mid-size or flagship missions, it really helps to know what it costs to do it. And the best way to look and kind of predict what those will be is to look into the past and see what it took to actually make the types of missions that succeeded. So understanding the cost history, and not just how much something cost in a lump sum, but when that money was spent, what those cost curves look like, and also as much as we can, breakdowns into what is the operation versus development cost versus launch cost and so forth. So really, it's important to be effective advocates to understand the history of what it takes to actually enable these types of missions. From a policy perspective, understanding cost is really important because it helps us understand what was important when. I have this big blue bar here at the bottom of the screen. Funding is really a proxy for political priority. You can say all the priorities you want, but when it comes to dollars, right, when it comes down to ultimately the zero-sum allocation of funding from the federal government, it really tells you what's important and what's not. So again, this helps you cut through the BS in terms of what people say they consider important and what is actually important versus when it comes down to spending. So looking at the history, how does planetary exploration funding change over time, both as a program, right, in terms of absolute dollars spent, and then also within planetary science, what destinations or what types of programs in planetary exploration received the money that it did get? And how does that change over time and why? And so there's a history that we've developed, of course, just looking at standard history about what types of programs were important when, and adding a layer of costing and expense information really puts down, I think, some hard numbers into quantifying the types of political support and what changes over time. And then, of course, it helps us, again, just kind of feeding into both of these aspects, both policy and advocacy. When did planetary exploration get its best budgets? Can we associate that with anything? What does that tell us about the point we're in now and where we might be going in the future? Are there aspects of planetary exploration that have grown more or less expensive over time? And if not, why? Maybe that gives us a chance to find ways to, become more efficient or cost savings, or that we just accept that there's minimum levels of investment required for this endeavor. And then, of course, what happens when funding goes down, and what happens, how does the program tend to react, and what happens as a consequence of that? Okay, so if we want to try to reconstruct this idea of what we've spent when over time, it seems like it would be a pretty straightforward problem, right? Like dollars are dollars, you can track where they go. There's whole buildings full of accountants doing this at the federal level. Why is this a big project that we had to put together? Well, one of the fundamental issues is that public reporting of this is really inconsistent and really scattered in various locations. There's no publicly accessible database already existing. NASA maintains internally detailed accounting information for missions to help them with internal cost estimation and analysis, but that's not public. That's only for NASA employees and contractors after requesting access. So it's considered really proprietary data because of all the contractors involved in it. So as much as I'd love to have access to that data, as much as I'd love to have free, have that data be free, we don't have that to work with. So the effort that really drove this project was, what can we recreate from public data? Other issues that we face with what has been publicly reported, you might say, well, what do we need to go all this detailed number searching? NASA puts out a press statement, on the launch of like the Perseverance rover, and it says, oh, it cost $2.4 billion. Why do we need more information than that? Well, this type of reporting, A, it's inconsistent. We don't know what they're necessarily including. Does it include launch? Does it include phase E operations in the prime mission? How does it include that number? And to what baseline, what year of inflation are they including that number to, right? NASA just didn't spend $2.4 billion on Perseverance this year. It was spread out since 2012. Inflation happens over that amount of time. So how can we keep that awareness? Can we break out more fine-grained detail and make these more fine-grained inflation adjustments to really be able to compare apples to apples over time, what one mission can cost compared to another? Operations beyond the prime mission are rarely publicly reported through press announcements. So what does it cost to actually run a mission beyond its initial science goal area? How does that overall impact the total mission costs? How much does that eat up of the overall planetary budget? We don't tend to know those numbers. And then, of course, there's just accounting changes that happen over time within the government about how they consider what is the cost of a mission versus not. And so these are some of the fundamental problems that we face when trying to just gather this data together to make it useful. So the solutions here that comes from this effort is to say, well, can we build this publicly available data set, or you build this data set using publicly published data, publicly available data? And how close can we come to the so-called actual numbers? The key here is that through the annual appropriations process, through the process by which NASA constructs its own budget request, submits it to Congress every year, and then Congress will take that and then appropriate money to it at the end of each fiscal year, ideally. This budget request is actually data rich. NASA includes not just the request for the upcoming fiscal year, they report on the so-called actual amount of budget authority that they allocated to each project in the 2 fiscal years previous. So the current fiscal year request that we have out now, for 2021, it reports what NASA has actually allocated to spend for each project in 2019. Using those numbers, you can actually go through the entire history of NASA's spending through the congressional budget requests and begin to pick out year-by-year amounts allocated to each project. There's a few pitfalls to this that I'll discuss later, but it's a very good granular accounting of the data. And then, for areas, because as I mentioned before, the type of accounting in these budgets changes over time. It really can change by administration or just type of template that they're using. We can use some press releases and public reporting, particularly at the analysis groups, all this, AG meetings that we see from OPAG, SBAG, VEXAG, and so forth. Sometimes they fill in additional levels of granularity, and we can pull various bits and pieces from those to help fill in some of these numbers. So really what this took was going through NASA's entire 60 or so years of budget requests to Congress, going through each planetary section, looking at the actuals and the requests for every single fiscal year, collating that all together, and then trying to normalize it out to make it consistent over time. And we'll talk a little bit about how we did that. The goals that informed this are also, I think, pretty kind of aligned. This is maybe why Chase asked me to speak today. One is that, this reflects the goals of the Planetary Society itself, which is fundamentally openness. We're a nonprofit and we share all of our data. We give a lot of it out for free, even though we ask people to be members. Our magazine digital version is free, our blogging is free, our articles are free. We want information to be accessible and used here, right? So we wanted to share this data in a useful way for the community, and also really share any editorial decisions that we made, how we normalize the data, and the raw data itself. So if you disagree with opinions that I had to make to collate this data together, that's fine because you can look at the raw data and come up with an alternative yourself that works better for you. So we're trying not to just give you a sanitized version of this data, we're trying to give you access to the raw data that informed this underneath. Again, trying to create and normalize the data in a smart way to make different eras and different missions comparable to each other to the maximum extent that we can. So we can really say, what was a mission in the 70s? What was a flagship cost to a flagship cost in the 2020s? Are those, how comparable are those together? And do we see changes over time? Really trying to use improved versions of inflation. Inflation is adjusting for inflation, right? That the dollar grows weaker over time. Is basically this idea that it's a dark art. There's no like perfect example of it, of how to adjust for it. But most people, I think, use what I would consider an incorrect application of the consumer price index, which is designed around consumer goods, right? If you want to track the cost of bread or milk over time, you use the consumer price index. But spacecraft and space missions to planets in our solar system, those are not consumer products, right? They're highly specialized outputs of a very advanced industrial process. And NASA has actually solved this problem in the office of their financial officer. They use a tuned price index called NASA's New Start Index, which really weights two things very strongly. It's basically combining a number of other inflation indices together and weighting them in a way to try to reflect, the true cost of the program. And what those are is that it really weights the cost of labor, right? The biggest cost of most of these projects is the cost of highly trained advanced labor, both in engineering and science. And then, of course, the cost of aerospace materials, the types of high-grade metals, alloys, and other things that go into building a spacecraft. And then with a dash of CPI and a few other things just to kind of round it out. But fundamentally, what you're really tracking with NASA's New Start Index, by weight of that index, is the cost of labor, which I think is a very good way to kind of adjust for inflation. So some of these numbers will look a little different than using CPI. But again, if you don't like what I did, you can take the raw data yourself and pursue it. And then again, to the maximum extent practicable, try to break out different aspects of mission development, right? So as many of you know, there's a period of mission development formulation where you're designing and testing out basic components of a mission, implementation where you're really bending metal and sticking it all together, and then operations where you're looking at the data return, hopefully, from a successful spacecraft, going out into the solar system, and what is the cost, relative to that, and then of course launch and so forth. So again, this will depend on how NASA has publicly reported it, but we try to capture that to the maximum extent that we can. I also want to encourage people, I guess, at this point to please feel free to chat in questions. Chase, I'm not sure how you're handling questions verbally or if it's just chat, but absolutely happy to address any and all questions as we go through this. So I'll leave it at that. So I'm going to walk through a few things here. You're welcome to join me. I'm sorry for this very long URL right now. We were actually here at the Planetary Society, speaking of an open meeting process here, or open planetary, moving our current website into a brand new CMS system, fully open source, top to bottom, that will ideally be coming out in the next couple of months here. Let's see, I do see a chat. Okay. So again, these URLs may change, but we'll put up nice redirects, but maybe in the next time we have this type of conference, our web developer can talk about the open source software stack that we're switching to. But for now, here's the URL. I'm going to switch over to that here on my computer. So here we are. Let's move this big. Okay. So this is the fundamental outline of the entire data set. For now, I'm using Google Sheets just because it's an easy way to enter data. It actually serves as a useful kind of pseudo backend database that you can pull into very easily from external websites. And I use some of this data to plot on our own planetary.org. It also makes, obviously, collaborating more easy, and you can download things in a number of formats to use, whether you want an open office format or Excel format or CSV format. Google Docs gives you that opportunity to use those. Ideally, in the future, I'd like to move to a more open source, maybe something on GitHub opportunity to host this data, but for now it's on Google Sheets. And I'll walk through some kind of broad aspects. So I have there's actually quite a few tabs on the sheet, and they're broken up into three main sections, or three types of tabs. One is summary tabs, and that's what we start with here. We see overall, this is like summarizing every major planetary mission here together through every fiscal year, just to kind of see the flow. And this is in alphabetical order. Perhaps it'd be more interesting to see it in a timeline order. You can move those around to see that. You can see the flow and cost per year unadjusted for inflation for every single major planetary mission from Cassini to Viking. You also have major things like planetary budget history. I'll go through some of these in a second. So summary tabs at the beginning, and then what I call mission tabs. I'll walk through these in a minute. Basically, every single planetary mission seen in that first list gets a breakout tab that breaks down to the extent that we can: launch vehicle, total cost, inflation adjustments, and then major notes and program highlights. And then at the very end, the raw data tabs for every single fiscal year that planetary has been spent. We pulled in to the maximum, again, extent that we could, maybe a more detailed year, the entire planetary program as requested and as actually provided in the NASA budget requests. So this is the raw data that you can pull from, that everything else in the spreadsheet pulls from, that you can then use yourself, so you don't have to rife through every single NASA budget request, though you're welcome to do that as well. So again, three types of tabs: raw data, mission tabs, and summary tabs. First thing, again, I think that's really useful to start with here. We're talking about some of these major issues, questions that I kind of set up to begin with. Let's just, for the time being, move this over here. Just the looking at the overall cost of what was spent and what was requested with planetary science at NASA for its entire history. As far as I know, this has never been compared before, looking at both the request and what was actually provided. That tells you two things. The request tells you what was requested by the White House, right? That's a political statement, really, more than anything. It tells you what NASA ideally would want after going through the whole internal policy battle on the administration side. The blue tends to be a proxy. It's not perfect, but a general proxy for what Congress ultimately provided, what NASA was actually spent on the program compared to the request. Useful thing in looking at this is that you can look at periods of time in planetary science's full history where the request deviated significantly from what was actually provided, and ask yourself what was happening during those periods. Of course, here the request tends to be, the early 1960s are always going to be a little wonky. We can talk about that decade specifically for people who have questions. But you can see, again, you can see some basic trends popping out of this data right away. First, I should mention this is all adjusted for inflation using NNSI. So this is, kind of constant dollars over time to 2020. You can see, of course, the 1960s, a huge spike. What happened in the 60s? Duh, right? The Apollo, huge burst of planetary missions. Interesting to see this immediate collapse at the end of the 60s as Apollo winds down. And then boom, you have another large peak up to about the equivalent of $3 billion a year. What was happening then? That was the Viking missions. A lot of you know that the nadir of the planetary program was in the early Reagan years. Historian John Logsdon has written a great chapter about this called The Survival Crisis of U.S. Solar System Exploration, where they were seriously considering spinning off JPL away from NASA to a pure DoD research center, and really canceling every single planetary mission there was. You can see that data, the funding really dropped down. And then the slow growth over time. Here's the interesting period of higher requests than what was received. This probably has something to do with NASA's growth during the attempted Vision for Space Exploration, or I should say the Space Exploration Initiative under George H.W. Bush with a renewed Mars push. And then this growth going into the early 2000s, this collapse again that we saw, a lot of you may remember. Here's the mid-decade of last decade of last decade that we just went through, the collapse. And then this incredible just steady growth outpacing the request every single year up until last year. And then you see a very promising growth curve there. Interesting to know again that we are currently in basically one of the highest periods of spending relatively adjusted for inflation of planetary science in history, right? It's comparable to that peak in the 70s and that peak in the 60s. And the question is, will this be a peak the way that every other peak as every other high point has been, or will this be a new normal as presented by this projected growth from the current president's budget request for the next 5 years? So that's something, again, to keep in mind. We're in a very good position in terms of funding right now. So I'll move on. So anyway, we have this incredible amount of data. These are effectively the summaries. You can see here, you can add a lot more interesting data. This is planetary science as a percentage of all US discretionary spending. Discretionary spending, not counting basically spending that happens by law, which is actually the majority of US spending every year. But this puts it into perspective. This is a function of the amount of money that Congress decides to spend every year. This is how much planetary takes up of that. And right now we're about a 0.2% of all of discretionary spending a year, but that's pretty good compared to kind of the lower points of 0.07 here, 0.05. So planetary, has done well, but also, again, helps put things into perspective. US is spending a very tiny fraction of its entire annual decision-based spending on planetary exploration. You can do lots of other fun things with this data set, having all of these programs here pulled in. I'll just mention a couple of things here, maybe to jump into a mission. To start with, maybe Cassini is a good long one. There's a couple of conventions that I use consistently throughout this data set to help understand how the data is interpreted. First is development. For every mission, anything in italics is going to be an estimate that's provided either through, it usually will note where it's coming from a president's budget request proposal for the out years, or from either calculations made by a press statement divided by years, kind of a simplistic estimates. A lot of times, the weakest data that's been shared by NASA over the years has been operating costs for pretty much every mission. It's very uneven in how they report that. So anytime you see an italics, it's an estimate. Anytime you see just a regular, it's an actual reported actual number to mention that. So that's just a All right, am I back? Okay, sorry about that. Go back to sharing my screen. Okay. Okay. So one of my favorite things we can do with this data set is start to do fun groupings of data to look more at other types of trends. I actually have maybe a slightly more easily understood version of this here. I will play this. So you can take all the data that we have and start doing things like grouping planetary expenditures by primary destination. So where did the money go of these big spikes that we saw in history? And I think we see some really interesting trends start to develop that reflect purposeful policy changes made to planetary exploration over time. So here's roughly color-coded by major destination, right? Prime destination, so the moon, Mars, Venus, Mercury, outer planets, and small bodies. You can see those big early spikes at the beginning of the planetary science history. You see, of course, here's it's all moon program in the 1960s. Your lunar orbiter, your lunar ranger, your lunar surveyor. All of these were robotic missions in the early 1960s. Very little else spent on other parts of planetary mission. And then, of course, look at how the growth of Mars came to dominate. This is the Viking. This is almost exclusively Viking, this one big peak. Viking was a Cadillac mission, right? It's 5 spacecraft, basically, they built. The most expensive planetary mission of all time, adjusted for inflation. It's a huge expenditure, and you saw that dominate in the early 1970s. But then look how quickly it collapsed. And then, of course, over the 1980s, what you really saw was outer planets kind of sustaining the entire program. Here's your Cassini bump, Mars Observer. But then the interesting part happens, starting in the 1990s and really extending towards now. as the budget has peaked in those multiple times, the peak that we're in now and the peak in the early 2000s, it's not due to one destination completely dominating. You see, of course, Mars really grow. This is the growth of the Mars program, where we ended up with something like 6 missions in about a decade, but it doesn't have anywhere close to the imbalance that you had in the early 1970s. What you're seeing here is the development of a balanced program, a multi-focus program that you're seeing now with relatively even distribution of money between Mars, outer planets, small bodies basically coming into existence over the last 20 years, and the moon making a big resurgence. And so you're seeing a much healthier, in a sense, program that we saw in these previous eras of planetary exploration that were dominated by these big, intense bursts of mission focus that then were quickly moving away to other areas. Other fun things that you can do with this. This is plotting, and sorry for the busy version of this, but this is plotting launch costs over time. Launch costs, the previous bane of existence to planetary missions. I'll look at that question in just a sec. Launch costs being the previous bane of planetary missions, right? Costing so much money over time. Well, here they are in context. Always really striking to me. Again, this is adjusted for inflation. Some of the stuff for the early missions in the 60s, very hard to suss out exactly launch cost per mission. So these are kind of average over for the Surveyor program per mission, average of lunar orbiters per mission, and so forth. But you see launch costs in the around $100 million a launch in the early 60s. And that's actually kind of what really we average out now, a little more expensive. You saw the growth. Here's your Titan boosters launching Viking and Voyager 1. Cassini, my gosh, the most expensive rocket you could choose, the Titan 4B, almost $700 million is what the program paid for that. And then, of course, what down here is amazing, the Delta II, basically enabling that burst of low-cost missions in the early 90s. Almost perfect alignment with the shutdown of Delta II and the growth of ULA starting in 2005, this inflection point starting to grow up in mission costs until now we're starting to get SpaceX coming in. Interesting thing from this type of plot, you see that SpaceX, with its low savings, its launch savings, is actually puts you basically where you were with the Delta II back in the 90s. So it's great cost savings, but it's actually not unprecedented in terms of planetary history. So all types of interesting things you can get from this. Let's see. We have a question. Let me just take a look at this. As much as I love Mars, I wonder how fair it is to just compare Mars and outer planets in direct dollars. One can scale budgets by kilometer distance. Let's see. Should we scale basically this budget chart spent by kilometer distance of research planet to be more fair? It would bring down outer planets expenses immediately. Well, that's true, as it would be designed to do. Again, I think you can play with this data quite a bit. The way that I kind of approach a lot of this is, sure, it might be cheaper per kilometer, but you're still talking about absolute dollars spent, right? So if Cassini becomes cheap per kilometer and you're going 3 billion kilometers out to Saturn, it doesn't change the fact that it's going to be a $3.5 billion mission of just expenditure, right? Congress doesn't necessarily care that it's cheap, per that type of metric. The absolute amount spent is still really important. And why do you see more missions to Mars? Well, it's certainly easier to get to, but that's not the only answer, right? The moon is the easiest, relatively speaking, right, place to get to. But look at how long this dead period was between the last lunar mission in '69 and the lunar prospector in 1996, which was barely a blip of a mission, right? So just because something is easy and cheap to get to doesn't mean it becomes the de facto focus. So again, I think that's an interesting ways to consider about how you can scale the type of expenditures by all sorts of qualifiers. And I encourage people to do that with the data. But fundamentally, I think the absolute expense is going to be really important because out of the total, if you're talking about a $2-ish billion or $1.5 billion overall budget average for planetary exploration over history, it doesn't matter what your per kilometer cost is. It really matters what your absolute cost is. Let me say this next question about the planetary large gap between requests and appropriations in the early 1990s. Which proposed missions target bodies were cut? Okay, so this was this period. This request balance here and the actual provided, what is the difference there? I think for sure I can tell you the first difference is craft. So the Comet Rendezvous mission that was originally proposed is Cassini and Craft were both supposed to use, what was it, like a Mariner Mark II common bus. So it's supposed to be a double mission. When Clinton came in, there was immediately, I think both missions started going over budget. Ultimately, NASA chose Cassini, committed to Cassini, and canceled Kraft. So I believe that's what that first peak is. I think that may be also related to the second peak, but I'd have to double check. But I think that's basically the cancellation of a major flagship, what you're seeing right there. One more question. If the absolute amount spent is important, why was the Delta II canceled? I'd have to remind myself why. Let's talk about the Delta II. I don't know off the top of my head. That's a great question. Someone may know rocket history better than I do. I don't know if it was not I know it was Martin Marietta, and then Lockheed merged with them, and it shut down not long after that, though they've been launching a couple of Delta IIs over the last few years from the original stock of rockets. It may have had something to do with the other, beyond NASA, there's the DoD launch market, which was the more dominating launch market at the time. They may have not used it as much. That's a great question, and I don't have a good answer off the top of my head. Worth diving into. Okay, let me jump out of these real quick and go back to the overall data here. Let's see. So we can go through a couple more key things here and then take a few more questions. Something also that's really, I think, going to be helpful, I'll be submitting a few white papers to the upcoming Decadal Survey process. You can break out data by decadal period, or what I would call it, Decadal Survey equivalent periods, right? So the Decadal Survey in planetary science did not start until 2000 basically, for the first 2002 report. And now we're starting the third iteration through that. But you can just break out those periods going back to the beginning of planetary exploration history, and you can really start comparing chunks of exploration and spending and timelines, destination in those periods. And you can kind of, again, see just different ways to look at that same data, what decadal periods were dominated by various destinations. I've done a little more work here. I'm almost complete with this new kind of a timeline view of comparing not just destination, but number of launches per decadal period. So basically number of new missions, the average development time from first time showing up in the fiscal year expenditures to the launch. And then, you can do some other numbers with it, but you can really see, again, this type of average launches. You can see the birth of faster, better, cheaper in the 90s, with going from 3 to 12 planetary launches compared to the previous period. You can see, again, that nadir of planetary exploration funding during the 1980s. You can see how, again, the change, what we've been seeing, this trend of growing development times, right? And the number of missions going down. Those two are obviously related. But again, what this kind of tells you, if you look at this, if you just ignore this kind of weird burst of missions during the Apollo period, which I think we should for historical purposes, weird time, a way to think about the next decadal survey is that at best, we'll get 8 new missions, or on average, I'd say we can expect 8 new missions in the next decadal period. And over the next, say, 30 to 50 years, right, we're talking about anywhere from 25 to 45 or so missions. And where are those 45 missions going to go, right? So interestingly, I think to kind of consider about how we are focusing our energies. It really is not that many missions, right? There's a whole solar system, and over 50 years, we're going to get maybe 45 shots at that solar system. So that's a very competitive, very focused area to, and I think a very helpful way to kind of define the future kind of allocation of missions in planetary science funding. Let's see, I've got some Q&As, I think. Let me see. Or no, okay, so it's the same questions. All right, so anyway, yeah, so again, think about this next decadal survey that we'll all be debating, or at least in the planetary community, 8 missions, right? And 4 of those, or a few of those, like Europa Clipper, have already been decided, right? Because there's a lag time, obviously, with that type of launch. All right, a couple other just useful things about how to use this here. Here's the original numbers, I should say. I've started a project of color coding various requests by the Republican or Democrat, red and blue, in the administration for the request. And starting with the 21st century, because it's kind of a time-consuming thing, going with either mixed congressional control, whether a Democratic House and a Republican Senate, for example, full party control over Congress, and whether red or blue. So trying to kind of coordinate colors in terms of seeing if there are trends there. I did start to track enacted funding, which is what Congress actually did in terms of not just, sometimes there'll be a difference between what NASA provides that'll be different than what Congress enacted. Biggest change was in 2013, actually. Sorry, I should say 2000, I believe it's 2013, where Congress, NASA basically reprogrammed about $100 million out of planetary science during the sequestration period and put it to other priorities. And those track in there too. So again, there's all sorts of, again, useful things we're trying to track. That'll be expanded out over time. Ideally, I'd love to get full congressional enacted numbers where they exist for the entire history of planetary science. Interesting thing is that pre-2010, it's actually quite rare for Congress to specify funding for planetary science. They would only specify appropriations at the science directorate level and not really put beyond just a couple of small earmarks, not really direct NASA how to spend money on planetary science. So actually what you're seeing here is an incredible increase in the amount of specificity that Congress is directing NASA on how to spend its money throughout planetary science and a lot of other aspects of NASA as well, beginning just in the last 10 years. Again, also somewhat interesting. We had a few ideas here I just want to share. I think, let's see. Oh, one thing that I should mention, for different types of missions, I think one of the most important, there's a period in the 1980s where the shuttle was the only launch vehicle for everything, basically. Whole separate history there. I did make an executive decision not to include space shuttle operations throughout as a launch cost for planetary missions. I can go into that more in depth if you'd like, but I did include the numbers for reference for anyone who wants to include operations costs for the shuttle to launch basically 2 missions, Magellan and Galileo. Other issues that we looked at here, I think worth mentioning, I've done breakouts by program. So we have Discovery program. I actually have a more complete program list here. If you want to compare Discovery to Mars, to lunar exploration, to research and analysis, and outer planets, those are all broken out in the modern era here. We've broken out programs by what would I say, the so-called golden age of planetary exploration that people, I think, is actually a dated term now. You can see the relative cost here of, again, the big lunar programs, the cost of Mariner here in red, Pioneer being these little bits on top of that. Again, you just see how the lunar missions dominated. Again, interesting aspects here about the trends of planetary exploration. If you can look at Viking as being this bizarre anomaly of planetary funding, and you can kind of plot that separately and just see that on top of the baseline planetary missions of everything that wasn't Viking, you actually do see an overall declining trend that continues into the 80s. So 80s was really just a continuation of a continuation of trends that began in the 70s that were kind of hidden by this incredible focus on this one-shot priority of Viking. Voyager kind of squeezes in there a little bit. I just kind of separated that out for clarity. But you see basically the idea of when you don't have balanced programs, you can have things popping in and out of existence with the overall direction of the program being very subject to change and loss. Let's see. I have a new question here. Ignoring the fact that political programs and ideals have changed, is there a standard stereotype that Republicans administrations are better from space? Is that actually true? I'd actually have to look at the data more comprehensively for that. I have a similar data set of NASA spending, and I would say generally for planetary science, it doesn't get to that level of focus, maybe more in recent eras, but that also might be driven by idiosyncratic reasons or reasons related to prioritizing planetary science over more ideologically unpalatable things like earth science. And so that I don't have a full answer to that. I'd say in general, what you see is when overall government spending goes up, there's more, the NASA's slice of the pie gets bigger, right? And so in the recent history, basically the 2 terms of Obama and Clinton, there was a lot of pressure to drive down federal spending, and so NASA spending overall went down. Mainly just kind of tracking that overall thing. So when you relax that requirements, is what happened under Bush and under Trump now, it's easier for more spending to happen. More granular than that, I would say requires some further work, and I would encourage everyone to use the data set and make a strong argument one way or another for that. So thank you, good question. Let's see, so I'm gonna just kind of wrap up with a few closing things here, and then I'm happy to take any questions or dive into any areas together. I just want to mention a couple caveats about things to consider, and I've written these out at the actual website itself, just as a reminder. First is we're limited to this public reporting of data, right? And what we're really getting is a final budget authority that NASA's being granted to these programs to spend the money. That doesn't necessarily mean that that money will be spent that year or as in the amount authorized. Sometimes there's money that'll go back into NASA unspent, and sometimes there'll be money spent over a couple of years. The outlays may be different than the authority. So this shouldn't be taken as the final answer. I've gone through and double-checked a various number of comparisons, and this is quite close, I think, to what final numbers tend to be to the ones that I've been able to see. And we're doing it consistently. So that's the other aspect. So we're always talking about the same types of numbers. And so it's good for comparative purposes here. But there's always going to be a little bit of a fudge factor. Again, we're only granular to the fiscal year. So sometimes a mission will launch, often a mission will launch not on the turn of the fiscal year. And we won't have the level of granular detail to say how much operations costs started that fiscal year mixed with development costs of that fiscal year. So there'll be a little bit of an uncertainty around those two numbers as well. Again, changes in accounting below a certain point, we don't know necessarily what's defined in a mission cost. In 2004, NASA began what was called full cost accounting for all of its projects, where essentially it assigns an overhead cost to any sort of internal project based on the proportion of the overhead that project consumes. So what that means is that missions after 2004 tend to look more expensive than missions beforehand because NASA was carrying a significant amount of overhead in separate books that are almost impossible, I think actually impossible to fully rectify the differences between the two. At the transition itself in 2004, they actually did direct comparisons between full cost and non-full cost accounting for a number of projects. A rule of thumb, but it's only a rule of thumb, looks at about a 10% difference. So you can say, on average, missions probably are about 10% more costly than they were beforehand. But that's just a fundamental break that there's no good answer for. And then again, normalizing costs can be arbitrary. So I want to highlight just a couple of important decisions. For example, where do you account for costs of the Pioneer program in the early 1960s, pre-Pioneer 10 and 11? The Pioneers that were basically what we would consider heliophysics now were actually considered planetary missions in the 1960s, except for 2 years in 1967 and 1968. So for those years, because it was so consistent to all the other years and because of Pioneer 10, we made decisions to include Pioneer in the planetary cost, even though it wasn't technically book kept there. Anything that happens, it gets a note to mention that, but it helps maintain a consistency of cost over year, because otherwise you would see a planetary cost line that would appear cheaper compared to the previous years because it's something we'll just book kept Pioneer in a different account that year. This mainly comes into relevance with launch vehicles. Up until really the full cost accounting in the 2000s, the cost of launch for expendable launch vehicles for planetary missions was book kept in a separate NASA launch account. They would helpfully list those costs, but they didn't count towards the total of planetary science budget. In order to maintain consistently with the modern era, every year going into the historical period where you have data, launch vehicle costs are added to the total of planetary science. So when you look at what that means is when you look at things like planetary science budget history here, and you see the request or the actual numbers, those will tend to be slightly higher than if you peek open NASA's actual budget document itself and look at the top line for planetary science. And that's mainly because we're just adding those launch costs, because it's, again, the cost of pursuing planetary science to NASA should include launch. Shuttle, again, weird exception to that, and there's only 2 missions that it really impacts. So that's something just to keep in mind. But if you do not agree with what I'm doing, the raw data we have also presented links to, and this is from NASA's History Office, has helpfully digitized every single NASA budget document there is. It's not easy to access, but we put up a Google Drive, and it's linked to off of our main website for the database, of every single NASA budget request since 1959 or 60, I believe, is there for you. So all the work that the NASA History Office has done, we've just shared that. So anyone can look at all this original data and validate or do alternative analyses to your heart's content. Going forward, I just want to give a few things, and I'll answer these next couple of questions. Is for communities. So again, this is, I consider, an open and ongoing project. And again, it's open data. So what I would love is if people have ideas for where to find data that is not well represented in this data set. There are periods of NASA's budgeting history where they really simplify and lose granularity, particularly, again, for operating mission costs. The late 90s through early 2000s, a period of particularly bad data. So any in terms of mission development cost, operations cost, research, and fundamental research for planetary science. If you have ideas or where you can find that, I would love to hear about it. Again, operations cost per year, mainly for pretty much every mission except for everything after 2013 is spotty. So again, if you have thoughts about how to do this, I'm open ears and encourage you to reach out to me. I want to, again, continue to refine and develop this. If you see things that need to be corrected, or you have questions or comments about what we've done, I'm obviously here to respond to any of those. So I believe that is the extent of the period where I'll just talk at you. I'm happy to answer any additional questions. And I think I don't see, yeah, someone said Viking was 4 missions. It was actually 5 missions. They built a 3rd fully ready to go landing spare. So that was, yeah, it's basically 5 missions, which is why it costs so much. They also procured a 3rd launch vehicle because the Titan III would have been its first launch. They didn't want to put its first launch on with Viking on it, so they procured a 3rd Titan III and launched it with a dummy payload just to test it first. So yeah, Viking was expensive for a lot of reasons. Not to mention it's just all those missions at one. Can I calculate an error on the 8 missions prediction for the decade? Sure. Yeah, I can do some more statistics on that, the plus or minus. It's the peak of, I think of it this way, the most missions in any decadal period was, I think it was 13, is that what it was, or 12 during the faster, better, cheaper era. And so that you can kind of see that as a potential upper limit, or an ambitious upper limit. Let's take a look at what that, yeah. Well, okay, really the peak was 27 if you include the 1960s. But again, you were just like hammering together some metal and just like throwing it at the moon. So again, I tend to discount that first early period of planetary science. But in the more modern era of how with systems management and modern engineering methods and systems planning and management, again, 12 is your peak, with 12, 11, and then your lowest was 3. So that kind of gives you a bound on how many missions per decadal period you can really expect. Let's see. Are there comparable data sets for space telescope missions? Unless someone else has copied my effort and done it with astronomy, not to my knowledge. So yes, that would be a further area of development over time, would be to expand this beyond planetary science. It's doable. All the data is out there. Obviously, it just needs the time and effort to do it. That actually brings me to my last slide. I forgot I should mention this. The Planetary Society pays me to do this, right, for you. So it does take a lot of work. And we've shared this data for free to everybody to use, to enrich this community and also to help us just be better space advocates, to be better planetary scientists, to help us just plan better. And so I just hope you consider joining to the extent that you can, or donating to help us do this job. We're an independent organization, so we don't take government money, and we aren't funded by corporate sponsors. We're only funded. I exist, or my job exists because of members who pay a monthly voluntary donation, or people who want to donate individually. So we depend on people. So I just make a quick plug for that. What share of total mission costs have launch costs made up recently? That's a good question. Actually, we could run that data almost at, I will have that data compiled in the timeline. So the next step I was going to add is the total mission costs. Off the top of my head, you can do a range, right? So Perseverance launch on an Atlas V 4.1 is about 250 million for that mission. And Perseverance as a mission itself is about 2.7, so it's about 10%. Then you look at something like DART, which is about a $300 million mission, and they're getting a SpaceX Falcon 9 for about 70 million, right? So in that sense, it's actually a higher percentage of the mission cost, but because DART is so cheap. But that's a good number to run, and that would be a good way to kind of compare that change over time. Great. Do I have any other questions? Yes, okay, one last thing I should mention here, a comment here. It'd be interesting to see similar data and analysis made for other space agencies and countries. And I completely agree. And it's fascinating. It reminds you just how open NASA is by publishing this data. There is no comparable public annual process by which other space agencies publicize to a very granular level how much they're requesting and how much they were spent on all their projects. Part of it is just a different function of how things are paid for. Obviously, European Union works in, European Space Agency works just in a very different way than NASA, right? They have committed levels of funding on 3 to 5 year chunks with different levels of mandatory funding and optional funding. There's no equivalent of an annual appropriation cycle for the European Space Agency. And so there's no equivalent of annual reporting in that sense. I would love to see data from ESA, for example, on its annual expenditures for ExoMars or any of its projects, but they don't exist. So that would be, I think, overall, what I'd like to do is find ways to reach out and communicate with a lot of different agencies to see if they can just voluntarily provide this. But at the same time, it's very difficult to compare, again, because of completely different accounting methods, what is included in what ESA would consider its ExoMars project versus what they would consider overhead or non-project related external costs versus what NASA defines for that, right? So a current example, ISRO tends to have very low costing missions at the moment, but it's very unclear where the overhead costs are going for those missions and how apples to apples can you make that comparison. So again, more openness, I would just encourage everywhere. That gives us a better chance and better ways to work with this. Let's see, I do see one more question. Yes, please push for more openness from your European members. Would you be willing to speculate about the unintended costs of very spiky funding? So training scientists when they don't have stable funding, is there a way to fix that? Yeah, so let's actually just look at this again. I think the early way of doing business here, where you had these big early spikes in funding, I mean, just as a good example, the Planetary Society was created in 1980 here as a response to this declining line, right? Bruce Murray, who was the director of JPL, and Carl Sagan saw this decline and they felt that, right? They were coming off this like Cadillac period of missions where they were doing Viking and Voyager, and you had Mariners and Pioneers going every couple of years, and it went to nothing almost very, very, very rapidly. So the Planetary Society was kind of created as a response to that to try to push back against that. And it's been this long process going back up, and you're seeing kind of here these spiky periods again. I think that really the benefit of what you're seeing now is this multi-balance program basically gives you many more, a much broader coalition to maintain consistent support. If you weren't on the Viking mission in 1975, you're not going to try too hard, right? If you're getting no other missions or don't exist as a planetary scientist. That was just all a very small Mars community, right? Same with the lunar community, serving a very different purpose for Apollo, basically. You could pretty much argue this is an extension of Apollo funding. But by having a much broader community where there are missions to Mars and to the outer planets and to small bodies and the moon, you suddenly have opened up a much broader coalition that is going to be interested in maintaining an overall program line, and many more options for scientists too, to broaden their perspectives, to do that kind of important multi-mission, multi-science, multidisciplinary work that planetary science does so well. And so I think what you're seeing is that there's probably not an accident that you're seeing this overall line generally increase over the last 20 years. And the question will be, can we sustain this high and not keep it, not let it become a spike, but become a new plateau? So good question. Do I have any more? Or I think I may be done. So again, thank you all very much for listening through this. Again, that people can hear budgets and their eyes can maybe glaze over a bit, but I think this is, again, one of the most fascinating aspects about the work that you do. And again, this is to make our job easier. So now we know if we want to kind of continue these types of missions, what the budgets they need to be, and then more data will derive out of the set, how long the average development times are, and where these costs are going. And again, I think the real problem, in a sense, for why you can't save money in planetary science is because, I'll save money or get cheaper, is because just the cost of labor is just really high. That's the one thing that does not go down. And so that's going to be an ongoing way, is how you can find ways to do more missions, either more cheaply or get the resources you need to do it. So again, I'm on the web and the internet. You can find me on Twitter, just my name, Casey Dreier. I also do a monthly podcast for space policy, just called the Space Policy Edition. Just Google it, and you can hear me talk ad nauseum about this for as long as you like. So again, thank you, Chase, for having me. And if you ever have anyone else has any questions, feel free to shoot me an email or hit me up online.